All right. Good morning, everyone. So until now, a lot of the talk has been around larger scale events. What happens in glaciers, rockfalls, landslides. But all of this, of course, will be determined to some extent by what happens at the material scale or at a smaller scale. And this is what I will be talking about today, which is rock damage and healing. I'll define that in a second, and trying to identify what happens at a microscopic scale to govern those damage and healing processes. So that worked 5 minutes ago. That's great. Right. So what do I mean by rock damage and healing? What I mean by damage is simply a change in material properties of the rock. Namely, what I will mean by damage is mostly a softening of some material. So here on this picture, you can see an example of an experiment that was made on a single bead of material, which simply gets a small weight dropped on top of it, and immediately as soon as the weight hits the material, then it gets softened and then recovers spontaneously more or less to its original level. So this depends a little bit. And most importantly, this is something that happens as a logarithmic-ish function of time. This is also something I'll be spending a bit more time on later on. So that was a lab experiment. Here's why is it relevant for field data? Well, first off, so those are dV over V measurements for aftershock sequences in Nepal earthquakes, if I remember correctly. And so you can see that every single time there's an aftershock, you get this sharp drop in velocity followed by a log-ish like recovery. And so currently there's no agreement on what exactly drives this. We're not even sure that it's exactly the same thing that happens in the lab and on the field, but I guess that's the same for all things seismology. But what we propose to do today is trying to figure out a little bit more about what actually happens inside of materials by looking at the anisotropy or lack thereof of such effects. To do that, we set up a relatively straightforward experiment. We have a cylinder of Bentheimer sandstone, which is nice, homogeneous, isotropic, no clear sediment layering, very porous, about 25%. And this sample we cover in piezoelectric transducers. Each of those has the capacity to act as both a P-wave source and receiver, which means that with about 14 transducers glued to our sample, we have quite a lot of source-receiver combinations to work with, and therefore quite a lot of path angles to explore. Our sample, we first set a confining pressure, so a hydrostatic pressure of 2 MPa. And on top of that, what we do is we apply a uniaxial compression cycle, very, very straightforward one. We simply compress the sample, leave it there for 3 hours, decompress the sample, leave it there for 2 hours, compress 1 hour, decompress 1 hour. I would like to emphasize that the amount of strain that we apply is tiny. We apply 10 to the minus 5 total strain, and just to make sure that we're well into the reversible damage process realm, and we don't want to induce any plasticity or any permanent damage to our sample. And for the entire duration of the experiment, what we do is we monitor the sample using acoustic waves, P waves specifically, and we do dV over V measurements. More specifically, we do those dV over V measurements looking at the first arrivals of those P waves. So this is not coda wave interferometry, even though behind the scenes we're using the same correlation technique, but we're not looking at the coda. And the whole thing lasts for about 8 hours. So again, just to emphasize, because I'm used to presenting this to rock mechanicists, this is where failure happens for Bentheimer, and this is where we are. So we are very far away from failure. We're less than 0.1% away. Like we're less than 0.1% of the failure strain. So now that we have our experiment set up, we have the whole thing happening, we do our TV over V measurements, and what does it look like? So first off, if we just take two transducers, so source of recombination for which the traveling path is horizontal, rather than 90 degrees with the loading axis, which is here in the dashed line in yellow, then it looks something like this. So at the very beginning, you have fairly constant velocity, and then so the shaded area in red means that we have uniaxial compression being applied. No background color means that there is no uniaxial compression being applied. And interestingly, so first we compress the sample, and what we see is actually a velocity drop that then recovers to what the value was before applying the compression, even though we are still maintaining this uniaxial compression. So this might come as a surprise compared to what Eric was telling us yesterday, which is naturally you compress a rock, you would expect the stiffness or the rigidity to increase, which is not what seems to be happening here. But then, even more interestingly, you remove the uniaxial compression, and the exact same thing happens again. We get softening, which then recovers to its original level. Yeah, just for reference, again, the amount of time that it takes. And then we compress again, we decompress again, and the same thing happens twice. So this is what we see for a horizontal wave. But now if we look at what's happening along the longest diagonal that we have access to, then we see something very different, but also still same somehow. Again, we have our velocity being around 0, which is natural because we're not doing anything yet. And then we compress the sample. And this time we have something that makes a little bit more sense intuitively, because we see that there's sort of a baseline shift. So it's like during this compression state, we have an overall increase in stiffness, but we still get those transient shape velocity changes. And again, the shape of the transients does not seem to depend on whether you compress or decompress the sample. But on the other hand, this baseline shift only happens when we compress the sample. So those are only 2 out of 150 something such measurements, but they're the most representatives of the whole class of behaviors that we actually have observed. And so now what we're going to do is, okay, there seems to be 2 pretty clearly different phenomena happening at the same time. So now, if anyone has glasses, if you remove them, then essentially the one on the top looks somewhat like this. And then for those who don't have glasses, you can just squint your eyes very hard. And then the one on the bottom looks something like this. To some extent, it's a very, very simplified view, but you'll see in the following slides that it's actually surprisingly effective. So what I'll do is I'll simply dub those transient shape, so damaging followed by recovery process. I'll dub that the non-classical effect. And the one that follows the shape of the loading, I'll dub that the classical effect. So in a little bit more detail, so how do we actually build this non-classical shape? So I said earlier that it was logarithmic-ish, but only going for a logarithmic function of time for the recovery, because there's 2 issues. 1, it diverges at 0, and 2, it diverges at a very, very long time. So to take care of this issue, what we do is we actually use Rohle-Sneeder's relaxation function, which is essentially an sort of like engineered relaxation function such that for intermediate times, it behaves like a logarithmic function of time, but it converges at both 0 and infinite times. Also, physically, what it represents is you just integrate a whole continuous distribution of relaxation times over a given range between a given tau min and a given tau max. So in our case, what we do is we simply assume that each of those recoveries is identical and that the effects do not add up. That is quite a strong assumption, but I'll get back to that in a minute. As for tau max, we go for tau max of 15,000 seconds. And something that's important to note is that this component is now defined. We use the same tau max for all of the relaxation times in the entirety of our data set. We use the same timings. So this component is now set. And know that we have that. So for the classical effect, we simply use something shaped like the loading. And basically what we're going to try to do is we'll take every single dV over V measurement that we have, the one you see on the left, and then just try to figure out, okay, so how much of the classical effect do I have in there, and how much of the non-classical effect do I have in there. To do that, we perform a simple linear inversion, and that will give us two coefficients, beta and delta, beta for the classical effect, delta for the non-classical effect. And then the end goal of this is to ideally get those beta and delta coefficients as a function of the angle, because what makes each of those dV over V measurements different is they travel through the sample at different angles with reference to the axis of loading. So if we run this inversion, so that's also something I like to emphasize. This is essentially only a two-component inversion. We only use those two parameters. Everything else has been set beforehand. The tau max, the tau min, everything is just set. So we really only invert for two components, beta and delta. And despite that, we can see that, again, those are only 6 measurements out of 150 something. We can see that despite using only two components, we're pretty good at describing the whole range of behaviors that we actually have observed in our experiment. Granted, the individual fits are not necessarily ideal. Some of those will be a little bit above, a little bit below. They don't exactly pass through the point cloud. So it might be a legitimate question to ask, okay, but what if we add more parameters? What if we invert individually for each transient and each static step? Well, it turns out if we do that, we get this, which is, I mean, arguably a little bit better, but for what we're trying to achieve, it's only marginally better. Arguably, the individual fits for each dV over V are a little bit more precise. You do get shapes that go nicely through the point clouds, but whether or not this is actually relevant for the overall conclusions I'm going to get to in a second, this is questionable. So for simplicity's sake, for now, I will simply stick to the two-component model I've introduced first. So now that we have that, for each of our dV over V measurements, we have, for each single dV over V measurement, we have one value of beta and one value of delta, each of which can be related to a single value of theta, the angle with the loading axis. And if we plot those, then it looks something like this. Granted, this is a little bit hard to read, but so on top you have the classical effect as a function of angle, and at the bottom, the non-classical effect as a function of angle. So reminder, so classical effect looks like this, non-classical effect looks like this. And so to help you picture it a little bit more, if we look at what happens around 90-degree angles, so horizontal sensor combinations, then you'll see that you'll have pretty low values of the classical effect, so you don't have this baseline shift, but you have a pretty significant amount of these transient components. So you end up with a shape like this, where you have almost pure transients recovering to whatever the elastic modulus happened to be before the stress change. And now if you look on the other side of the graph, then in that case, you'll see that we have classical and non-classical components in about approximately equal quantities, which means that you not only have those transient shapes, but you also have this significant baseline shift, and looks like this. And now to further look into the anisotropy of this, what we do is simply we fit through those data points using a classic transverse isotropy law, so U sine squared theta plus V. This is something that shape-wise can be related to the expected load-induced anisotropy in an elastic material. It's also something that is shaped like a sine squared. And so if we look into that in a little bit more detail, looking at only the classical effect first, we see that there's a pretty clear anisotropy of the effects. Second, we see that we have effects that almost vanish along the horizontal, which again matches what we've seen in the dV over V measurements, where you have those transients going back to pretty much their origin point before the perturbation. And three, that's something that's a little bit implicit in the way we built our classical component in the first place, but that's something that is key to remember. It's that whether we uniaxially, for the uniaxial part, compressing and decompressing the sample has opposite effects. If you compress it, the sample stiffens. If you decompress it, it softens again. For the non-classical component, however, it's a very different story. We have much less clear anisotropy. We have a significant effect in all directions for the sample. No matter which source-receiver combination we look at, there's always a transient component. There's always a significant damage and recovering process. And third, again, that is something that's implicitly contained in the way we build the component. Compressing and decompressing the sample has, qualitatively at least, identical effects. It will always induce damage followed by a recovery. So now if we summarize all of this, because the end goal, again, is to try to figure out a little bit better what happens inside of our sample. Yeah, just as a parenthesis, this is what we've done with the 2-component model, running approximately the same analysis with the 11-component one yields essentially the same conclusions. So again, one more argument in favor of just using 2 components. So now to summarize what's happening inside, or at least getting some insight. So we attribute those effects to 2 very different things happening. So I'll get to that in a second again. But if we look at the classical and non-classical effects, so clear anisotropy makes sense for the left. Horizontal contacts will be affected differently. I mean, waves traveling at different angles will be affected differently by those horizontal contacts. Whereas if we look at sheared contacts along oblique planes between grains, then one can easily imagine that no matter which angle the wave is traveling through the sample, it will meet approximately the same number of oblique points of contacts because they're distributed evenly through the sample. Another point, so the fact that the effects vanish along the horizontal, again, makes sense for the horizontal contacts because there will be a lot more influence of the vertically traveling waves than for the horizontally traveling ones. Whereas for the sheared contacts, again, no matter which direction, it will be affected to some extent. Also, the fact that the compression and decompression have opposite effects. For the opening and closing of contacts on the left, then it makes sense that whether you decompress or compress, then you will have opposite effects. Whereas you can get shearing along contact points, along oblique contact points, no matter whether you compress or decompress. It's going to slide across essentially in the same way. And finally, that's something that we'll look into further at a later time. The shearing along oblique contacts essentially leads to the breaking of some atomic bonds between the grains. And if we look at rate and state friction theory, we get a natural explanation for the logarithmic-ish recovery time, which corresponds to the log time growth of surface area once it's back into place, essentially contact aging. And yeah, so those are the main takeaways in process. Of course, there's a lot more to be done, but that's about it for the moment. Thank you.